Although we generally think about ASAP as being a ray tracing program, ASAP also includes a couple of algorithms that can be used for propagating wavefronts. These include a Gaussian beam decomposition algorithm, which is for propagating wavefronts through large structures. There's also a beam propagation or BPM method for propagation in microstructures, single-mode fibers, grin fibers, and other small structures. For those applications which require this type of analysis, all you'll need to do within ASAP is to define an appropriate Gaussian wavefront. In this particular case, we'll take a look at the wavefront propagating through a ball lens, and we simply define a Gaussian beam of a particular wave size, and then we'll propagate that Gaussian beam through our optical system. So what we can see is the beam waist at the input to the system, and this is the beam as it goes through the half of the ball lens. I'm going to take this a little bit out of scale so we can see it a little bit better. And what we see is the shape of the wavefront as it's propagating through the ball lens. We can use our cursor to get information about the size and intensity at any location within this system. But instead of simply propagating rays, ASAP is actually propagating through the scalar field of a Gaussian beam. This is necessary when you have small structures such as single-mode fibers, when you're doing fiber coupling efficiency calculations, and other optical structures that are small but large relative to the wavelength.